I'm really going to focus, especially for this audience, on some of these kind of core cognitive abilities that in some ways maybe could be thought of as a kind of micro foundation for the kinds of scaled up collective intelligence that we see, but focusing much more on the kinds of common sense intelligence we have when we're interacting with others or interacting with small groups of individuals that can, but that ultimately can lead to more scaled up mechanisms. So I just want to start with this observation about the ubiquitous nature of cooperation. Essentially, you can find cooperative behaviors across the animal kingdom. So in this example, you can see these are weaver ants, and they divide tasks so they can like pull leaves, use them to make silk in different ways. Here's a nice video, which I like because they're kind of using their bodies and connecting them up to create a bridge to cross this gap, which is far greater than the size of any one individual ant. So they can kind of collectively solve a problem that no individual would have been able to solve on their own. And we can see that again as we get kind of further, even further closer to us in the animal kingdom. So here's a pack of wolves, and they're able to take down a much larger animal as prey. And one of those animals alone couldn't do it, but when they work together, they're able to figure out how to, basically take down this large, looks like a buffalo. And then finally, as we get to more sophisticated kinds of machine intelligence, of AI systems, we're also faced with the possibility of more sophisticated kinds of cooperation, the cooperation between machines and machines, or between humans and machines. And I think these are some of the most exciting new phases that of cooperation that we might get to see in the future. But even across the animal kingdom and maybe in some of these sophisticated AI applications, there's still a really distinct role for human cooperation. We have distinct ability to cooperate with others. So I think Josh showed this video yesterday, but even a young child can cooperate with scale, scope, and sophistication that exceeds all known non-human intelligences. Here, a toddler barely able to walk can spontaneously help an adult to complete a task. This is from Felix Wernigan. Here's an example where 3-year-olds can negotiate how to divide the fruits of their label fairly. So they both pulled the string, but one kid got a few more treats than the other, and he quickly figures out he can share this with the other to make a fair split. And then as you get older, children can solve a variety of challenging tasks and social dilemmas using all kinds of sophisticated norms and rules, turn taking, rules of fairness, things like that. And all of these are really just a prelude to the unprecedented levels of cooperation that underlie things like social institutions, social contracts, government, science, technology, morality. In some cases, these cultural products may involve millions of unrelated individuals in different locations who will never meet and may have only met once. And so I think, in a large way, this idea of multi-agent common sense is to try to figure out what are the kind of core pieces of social intelligence that allow us to distinguish ourselves from other animals. And then also, how might this kind of common sense be used to design different kinds of AI systems that are equally capable of interacting with us as true partners in action and in thought. So that's kind of the big broad framing. But I want to just kind of zoom in on an area which I think will be quite familiar to this more mathematical crowd, which is to start with some simple toy environments. And just to focus on, we have this amazing ability to cooperate, and we see that across the animal kingdom, but cooperation is challenging. So collectively, we might all be better if we cooperate. For example, if we all pay our taxes to the government, we'll all be able to participate in the collective benefits that governments can provide. But if I withhold my taxes, well, I keep the money and still get the collective benefit. So there's a tension between what's good for the individual and what's good for the group. And this has been sometimes called the tragedy of the commons. And it's been, and the idea that these two pieces are in tension really goes back many years. How can we reconcile the existence of all the cooperative activities and behaviors that we see in the world with the kind of logic of individual rationality or evolutionary selection or natural selection at the individual level. And this question's really been the pursuit of game theory, evolutionary game theory, economics. This kind of rational agency, individual agency assumption permeates many different fields in the social and behavioral sciences. And so again, to kind of zoom in, we can study this tension in a very simple environment. So this is the prisoner's dilemma. And I'm going to assume that most people have some experience with these kinds of objects. So these are matrix form games. And in the prisoner's dilemma, there's really player has two options. They can either cooperate or they can compete. I'm going to say that. And if they both cooperate, that's what's best for the group. So in this case, they both, let's say, be getting 7 units of welfare. But if the other player cooperates, well, I'm still better off competing because I'd get 8. And if the other player is competing, I'd also be better off because I'd be getting 4 instead of -1, which is kind of like the sucker's payoff. And so there's in this kind of simple game, we get this idea of the challenge of cooperation, and this has been studied again for many decades. One popular strategy that has emerged is this notion of reciprocity. This is how one way in which many organisms, including people, solve these kinds of social dilemmas, which is we can think about, well, I'll cooperate with you if you cooperate with me. This kind of simple notion, which has been encoded in strategies like tit for tat. And it's a very simple strategy. You can write it down as a finite state automata, where you start off in a cooperative state where you play cooperate. And then after that, you just copy whatever the opponent previously played. So if they then defect or compete with you, then you compete or defect back, and then vice versa, you can switch back and forth. But the challenge of these kinds of simple algorithms is that they hint at this idea of reciprocity, this much more general notion of what it means to cooperate, but don't actually explain the real general challenge that is faced by many forms of natural intelligence. So, for example, the human concept of tit for tat is far more general than what these automata strategies suggest. For example, tit for tat doesn't actually know anything about the particular payoffs of the game. It just knows about the labels of the game, that they're labeled cooperating. So, and then when you change that game in subtle ways, where let's say you want to cooperate, but it's sequential, well, one player is going to play first, or there's some subtle coordination issues, or there's some noise in the environment, you then end up with this huge host of different strategies in the bottom right, where there's not really just one algorithm that can explain this kind of cooperative behavior, but rather many. And so then the question becomes, well, when to do one and when to do the other. So really I think what I'm hoping to show you some hints at is what a reverse engineering account of these kinds of collective intelligence that might lead to large scale cooperation might look like. And so in contrast to these finite state automata, how do we as humans collaborate and cooperate so flexibly and so robustly? We don't do it because we just have a huge repertoire of behavioral reflexes like these automata models might suggest, but rather we have much more flexible and general intelligence that allows us to succeed. This is the sense in which humans are in some ways super cooperators, that we can cooperate in so many different contexts. And so I'm going to touch on, I think there's really 3 levels of explanation that are important for understanding this kind of collective intelligence, the cooperative side. And I'm going to focus most of the talk on one with some hints at the other 2. But starting from the kind of top down, I think we want to be able to understand, why, what are the evolutionary origins? How might we have come to these kind of cognitive structures that might enable flexible collective intelligence? I'm not going to talk much today about this second piece, which is how do we then acquire cultural knowledge about the particular norms or moral values of a particular society or setting that can then be used to rapidly cooperate in all kinds of novel coordination contexts. And then finally, and I'll spend a little bit of time thinking, first starting off on this, which is using all of this knowledge, these cognitive structures, and some of the knowledge that might be learned in development to then have a broad capacity for cooperation in the moment. And what that really means is the ability to cooperate in a much more general sense than tit for tat can, in a much wider variety of contexts. And I think there's going to be a general theme, which is that in order to build successful cooperative agents, these agents need to be able to have a very rich and abstract understanding of other agents. So who's a friend and who's a foe? And that inference problem ends up being a kind of key piece that I think we'll see at a variety of different places. And I'm going to try to do a mixture of some math, but also some cognitive sciences as well. The math will be actually relatively light. Okay, so the first piece I want to talk about, and I'm going to spend a little bit of time here, is to talk about cooperation in contexts that are, in some sense, much richer than a prisoner's dilemma. So we've been calling these naturalistic games, but they're essentially, if you're familiar with the reinforcement learning literature, they're called stochastic games. They're spatially, unlike a prisoner's dilemma, they involve a generalization to have certain levels of spatial and temporal extension. So players don't just have to pick cooperate or compete, but rather have to pick a whole plan of actions. And so let me just first explain the rules of how this works, because I think it'll help explain what's going on here. So players control these little circles, and the goal is to move the circle avatar into a square of its own color. So you can click where you want to move, or each agent moves simultaneously. Each agent will move simultaneously. So here would be one example but if they both try to move to the same square, one will enter that square and the other will be kicked out. So here's an example of if they both try to move to the same square. You can see the blue guy made it, the yellow guy didn't. Okay. So movement's costly, so you want to try to get to a goal in as few moves as possible. But moving to a square of your own color, and moving to a square of your own color gets you the points that are in that square, in this case 10, but that also ends the game. So here's what would happen if the blue player moves to the end goal, then now the game is over. The blue player moved twice and scored 10 points, so ended up with 8. The yellow player tried to move once, so they lost a point, and then they didn't move again, so they just ended up with -1, and now the game's over. So we can think about, what might a cooperative strategy look like in a game like this. So here'd be one example where they both move to the ends of the environment. Competition, on the other hand, might look something like this. We looked at one example, but here might be an example where maybe blue's wanting to cooperate, but yellow just goes to the early goal and gets a higher reward. So we can go back and look at this game and think about it in the same kind of context of the prisoner's dilemma, right? Where we have two kind of higher order actions, cooperate and compete. And then the question is, now we can just apply the same logic that we did before. So if we map cooperate and compete into these, map this complex spatial and temporally extended game into these more abstract actions, we can get back to the kind of prisoner's dilemma game, right? But really, all of that mapping is being done by the intelligence of us, in this case, our perception of these environments. So, for example, you're not ever just given this grid. Instead, you're given a whole complex set of plans that have to figure out, well, which of those plans are jointly cooperative, which are jointly competitive, and not all cooperative plans are created equally. So there's going to be a challenge of coordinating actions across different cooperative plans. And I'll show some examples of that in a little bit later. So we started with this problem of prisoner's dilemma, and it was answered repeated prisoner's dilemma. In some sense, it was answered by this simple finite state automata like tit for tat. What might a similar strategy look like for a game like the one I'm showing here? And I'm just going to spend a little bit of time sketching this out before moving to the evolutionary piece. So what are the kind of key cognitive features that are going to be a satisfying answer to this question? The first is, I think we're going to want to have the social reasoning happen at the level of a high-level abstract plan. But it's not enough to just reason at the high level. You actually have to be able to implement cooperations. You have to be able to implement those actions at a low level to achieve that abstract goal. So abstract goal here, I'm thinking cooperate, compete, and we can think of many others as well. But which plan I try to do is going to depend on the intentions of the other players. So if I think that you're trying to cooperate with me, I might then cooperate back. If you're trying to compete with me, I might compete back. But I never observe your abstract goal. Instead, all I observe are those low-level implementations of your behavior. So I should be able to infer what your goal was in order to do the social reasoning on top of that social reasoning on top of it. And then finally, and I'm not going to spend too much time talking about this here, but cooperation has to be coordinated across agents to realize efficient outcomes. And that's really important for making cooperation efficient. Okay, so essentially what I'm going to do is I'm going to introduce two modes of planning, a cooperative planning mode that actually builds on some of the work that was or is related to some of the work from one of the presentations yesterday. And the first mode is this competitive planning mode. And what it does is it's essentially a probabilistic planner that takes in the intention that I want to compete and also the state of the situation. And then it's going to give me essentially a distribution over actions where the better actions are weighted higher that say that realize that competitive intention. And essentially what the competitive planning mode is going to do is going to be a reinforcement learning generalization of what's sometimes called level K reasoning. In the behavioral economics literature, it's called cognitive hierarchy. I think it's related to the conjectural variation approach that was described yesterday, but I'm not 100% sure because that was new to me. But what the general idea is that you start off with a level 0 player as a model of what the other player is going to do. And that other player essentially doesn't reason strategically at all. They just assume the other player either isn't there or is moving randomly. And then just now that they know what the other player is going to do, they're in a single agent environment and just optimize against that static player. What we can then do is build a hierarchy of more and more sophisticated agents that then best respond to those, where the K agent best responds to the K-1 level agent. So here's an example of that in the language of Q learning, where you're defining the Q values for the level K player in terms of the environment with a transition function of the K-1 player. And then all actions are going to be made by taking the softmax. This is just a Boltzmann distribution of those Q values to define the action policy. And so what that does is it says, well, if you do this, then I'm going to counter you in that way, right? That's this notion of best response and iterating that recursively over time. And here, okay, so here's, I think, one of the first key things that we might think where the kind of distinct kinds of cooperation that people have is different from just these very basic notions of you do this, I'm going to do that in return. One is this idea from Michael Tomasello, this idea of shared intentionality, which is that, and he writes, humans are able to coordinate with others in ways that other primates seemingly are not, to form a, quote, we that acts as a kind of plural agent to create everything from a collaborative hunting party to a cultural institution. Likewise, in the philosophy literature, you have Michael Bratman and John Searle saying, talking about this different notions of shared agency. So, I go to New York and you go to New York is very different from we go to New York, which might even be different from we go to New York together. And this idea that when we're making plans with others, those require us to mesh our plans in oftentimes in sophisticated ways. And then Nick Chater also has this notion of virtual bargaining, that we might behave on the basis as if what we would do if we could come to an agreement and negotiate over our plan, we could then act as if we had done that negotiation by having a sophisticated model of what the other player might do. And I think all of these ideas, which are quite qualitative in their nature, all point to this really distinctive computational mechanisms that might be useful for planning with others. And so my goal here is to try to formalize these ideas into what might be a basis for this kind of cooperative common sense. Okay, so same idea. We're going to now have a planning program for cooperative action. And instead of having it be based on best response, it's going to be based on this idea of planning together. And so what the agents are going to do is they're going to kind of take a step back from their particular role in the environment, and they're going to look at the environment as if almost like they're a puppeteer. So they're going to say, well, what is the goal of this group? It's to score as many, in this case, it's quite simple. It's to just score as many points as possible from some joint utility perspective. And then they're going to pretend as if they have joint control, like a puppeteer that's able to control both dots in this particular environment. And so they're going to be able to act as if they can control both agents, and then using the same kind of basic single agent formalism, because now it's just one agent controlling both players, find a policy that then supports this that can optimize this collective reward. Now, this joint agent or we thinking from the view from nowhere is of course just a fantasy. It isn't actually, they don't have joint control. So each agent can then look at that joint policy, marginalize out the other players, and then just play their role in that joint plan. Okay, so essentially you can think about the cooperative planning mode as each agent says, well, what do we want? How would we plan to achieve that? And then plays their part of what that joint goal, that joint planner would do. So, okay, so we have these two modes of planning, a cooperative competitive one, but then there's the question of when to cooperate, when to compete. And now this is this part about how to implement these abstract social goals. So I think one thing, and we're going to see this theme again in a later part of this talk as well, that we can build on these models of action, how agents might behave, and using Bayes' rule, invert those plans to use them as models of action understanding. So this is just applying Bayes' rule. So if each planning program says how likely is an agent to act given that they have a certain goal, like cooperate or compete, with some prior, I can then use that to get a posterior over how likely is the agent, given that they took a certain set of actions, how likely are they to be competing or cooperating? Okay, so this is kind of an important, this is how we can take these forward models of behavior and then use them, leverage them for models of how agents might understand others in these complex and abstract ways. Okay, so and then the simple idea here would be: if I detect you're cooperating, reciprocate cooperation. If I detect that you're competing, reciprocate competition. But it's in an abstract way where it's directly grounded in the actual values of the game rather than just the labels of the game. Okay, so here's just some data. What we did is we collected play from people playing this particular game 30 different times. And what I'm showing you is a histogram of how often people, a dyad of agents cooperated. Some agents never cooperate, some cooperate all the time, some are in between. And what I'm showing you is a model trained on those same, for each player trying to predict what's going to happen in the next round, that same distribution. And you can show that our model basically captures the distribution of these populations of players. When we look at that at a specific level of granularity, so like, are we predicting actually who cooperates? The model predicts who's going to cooperate in this particular setting, and not when we lesion it. So when we say, okay, let's just try using only the cooperative model or only the best response model, it's not able to capture this kind of variation because it's not able to move between those two plans. I want to get to the next part, and I don't have much time, so I'm going to just skip through this quickly. But this is just showing that we can use the same model of trying to predict what people will do, to also model people's judgment. So they then watched a little video of agents moving and and then judged, do you think they're cooperating? Do you think they're competing? And you can see the model quite closely corresponds to what people's judgments are. So we have a quite close correspondence. I'm just going to point to a little bit of other work that on the same idea. So also thinking about what should we do? What happens when the plans get really complicated? So here's a cooking game based on the game Overcooked, which is a fun video game. And here there are many ways you can solve some of these challenges. You could work together, you could work separately, and the same idea applies. This idea of is agents thinking, what should we do as a group? And then how I'll play my role in that joint plan. So here it might be divide and conquer. You do something, I'll do something else. Or no, let's like chop the lettuce together and things like that. And we developed this model of Bayesian, we called it Bayesian delegation, which allows agents to allocate plans to each other without any kind of communication in the loop. And it builds on some of the same ideas that I presented earlier. This idea that agents should think, what should we do as a team to succeed, and then divide up the work based on what we should do. And if both agents are reasoning with that we mode of reasoning in mind, they can be quite successful. I don't have time, and this is just showing kind of some of the quantitative results from these experiments. I'm not going to go deeper into this, but our model is able to cooperate and efficiently coordinate in a wide variety of contexts, while a bunch of different baselines fail. I also don't have time to point to some other work, but we also have looked at these same ideas of planning as a we in the context of communication. So what should I tell you, or what do we need to know as a group, right? So in all of these contexts, all the agents observe everything about the world. The only thing that's uncertain is about what's going on in the heads of the other agents. But in many contexts, the world is partially observed. And so each agent one agent might have information that is beneficial to the others. And so when you have a communication channel, you could think, well, what do we as a group need to know collectively such that we can solve this task most efficiently? And so we use that same idea of planning as how well would we do if we knew that, to then think about, well, then what should I communicate to you such that we can realize that kind of we planning? Okay. So in the last piece I want to show is some more recent, but I think currently unpublished work looking at that last question. How might these kinds of structures evolve? And this to kind of close the loop on not just this is a good idea because we can get better performance, but this actually has some stability when you're faced with all kinds of adversarial perturbations. So one of the key things that we wanted to probe, which I think in some ways the other studies didn't look at, is that humans are faced with essentially tons of variation. We never play the same game twice. So instead of just playing a repeated prisoner's dilemma, or even the game I showed you before, playing that 30 times, in this context, people are playing a new game every round. Instead of playing a single game, they're essentially faced with like a game engine, an engine that generates new games. And we designed this setting to kind of explore the wide range of different games that are possible. So within the kinds of games that can come out of this game engine are things like Prisoner's Dilemma, but also different kinds of variants. So like games where I can pay a small cost to help somebody else out, or games where it's no cost to me, but I have to choose, should I give a reward to player A or to player C, or all the different hybridizations of those kinds of approaches. So, so if before we had this challenge of Prisoner's Dilemma, tit for tat, this stochastic game, and this we mode of thinking, here we can ask, what's the right kind of model to start thinking about a situation where you're never playing the same game twice, in an evolutionary robust way. And so what we're going to do is to try to develop a set of models towards this, which develop into an abstract theory of reciprocity to allow for agents to cooperate quite robustly. So we're going to endow different kinds of agents with different kinds of utility functions. So we can imagine a selfish agent that only cares about its own reward, an altruistic agent which just cares about the reward of the group. This is basically saying, take my reward and then just add in the rewards of everybody else. But then, the question is which of these are a good utility function? Is the selfish agent a good utility, or is the altruistic agent a good utility function? Because when it plays against itself, it'll achieve the highest score. Or when the selfish agent might do better when it's playing against anybody else. So, but maybe not so well when it's playing against itself. So, how do we know whether a utility function is good or not good, especially in a world that is itself adaptive and changing over time, as any social environment is? So, just to give a kind of a qualitative flavor of how these evolutionary approaches look like, you can imagine starting out with a world that's entirely filled with altruistic agents, but then just by some random mutation, one agent might become this selfish agent type. And base after that happens, some of these other agents might say, hey, that one selfish agent got a higher reward. I'm going to copy I'm going to copy how that agent's playing. And now you have more agents playing selfishly, but the total reward, the total welfare of this population is going down as more agents switch to this selfish type. So essentially you get to this kind of like equilibrium where nobody's acting in a cooperative way. So I like this quote from Steve Pinker, which basically talks about this challenge in the pithy way, which is that natural selection doesn't forbid cooperation and generosity. It just makes it a more difficult engineering problem. Okay, so what we're going to do is we're going to introduce this new kind of, this new agent, this new kind of reciprocal cooperator. And the way that they behave is that they take they care about their own reward, but they also care about the other rewards that the other players will get, proportional to the probability that they believe that those other agents are also reciprocal. So this is almost like a kind of program equilibrium where these reciprocal agents are trying to rationally figure out using Bayes' rule who's like me, because person's going to be a reliable cooperative partner. Okay, and so then but to do that inference requires me to infer your type. I don't observe the types of these agents. You have to infer it from behavior. So again, we're going to use the idea that models of action can be models of action understanding. So same concept, given, I'm going to take this idea of softmax utility and say, well, that's the probability that I might take a certain action given that I'm a certain type. And then that theory of mind is then, the probability that is the posterior I can then compute, which is the probability that you're a certain type, which is what I want to condition my behavior on. I can use my action model, the likelihood, and some priors to figure out what type you are. Okay, I'm going to go through this a little bit quickly because there's some problems if we just apply this naively like we did in the last. If I just start with some prior, let's say I think, I'm just going to start off with the optimistically thinking that you're reciprocal to start off with. Then when I see that A is nice to B, I'm going to think A is more likely to be reciprocal or altruistic, but not likely to be selfish. So, okay, Bayes' rule in action. If I see A be mean to B, where that means like withholding a benefit, there's maybe some chance they're reciprocal, but most likely they're selfish. So, okay, everything's looking good here. But what happens when we go one more time step into the future, where A is mean to B, but now, and so we have now this is our prior, and then B is mean back to A. Well, what we should think is, well, B could they could be selfish, but they also could be reciprocal. Instead, what we get is this overwhelming inference that B is also selfish. And that doesn't really make sense because it's just naively thinking, well, doing the mean thing is what the selfish agent is more likely to do. It's not updating the fact that B has now a new model of A, which is that A is not likely to be reciprocal. And therefore, if you're reciprocal, you shouldn't also be nice to someone who's not reciprocal. So we need to apply some kind of recursive theory of mind. So agents need models of other agents, and there's many ways you can do this. You can have higher orders of belief. That's what I'm showing here, where A is a model of what B is thinking. And then you could kind of extend this out where they might have multi-lested models of belief. But ultimately, this is going to scale quite poorly in terms of the number of models that you have. The size of this data structure is going to grow exponentially with the number of interactions as the history grows, if you want to make it exact. And if you just kind of pick a finite cutoff, you get all kinds of problems computationally where the beliefs quickly diverge and become unstable. So I'm going to just quickly introduce a different mode of thinking about tracking knowledge in this setting. So we've been thinking about it as a kind of joint belief, where you're not thinking, well, if I know you, if I know you, I know what I know, I know, etc. Instead, agents are going to track what we know, and what that essentially is saying is that agents are tracking what the joint knowledge or common knowledge is of observations. Lets these agents then figure out what two different sets of agents know, and instead of having this infinite exponentially growing tree, you instead end up with a partially ordered set. So here in this model, A's model of B's beliefs only depends on the events that are jointly observed by A and B, because what else could determine those beliefs? And therefore, A's models of B's beliefs are identical to the beliefs that an external agent, kind of in this view from nowhere perspective, would form had they observed what was jointly observed by those two agents. And so that lets us massively compress this data structure into something much more compact. And it simplifies the reasoning about beliefs and updating about knowledge in groups. Okay, so I don't think I actually have much more time. So I'm just going to go quite quickly through the rest to show that this corrects some of the problems that we saw before. So now we get these kind of common sense inferences about who's good, who's bad based on behavior. It enables agents to rapidly infer who's who over time. So when paired, let's say, with a selfish agent, agents can really quickly figure out just after a few interactions, yeah, that agent's selfish. So they can do kind of rapid few-shot learning, and they can do that for some of the other agent types as well, although it's slower to distinguish reciprocal and altruistic from each other. And then we can run evolutionary simulations and look at what I'm showing in these kind of plots, which I'm going to show a few of, are the as a function of some environmental parameter at the bottom on the x-axis. So the more times this game is repeated, how likely are we to get these different types of agents? So the more area in the blue is more likely to more reciprocal agents. And after a certain set of a certain number of repetitions, we get the reciprocal agent as the dominant agent in the population. So essentially, this agent is a successful cooperator in this game engine environment. And it's also quite robust to noise. We can add a lot of noise into this environment and still get relatively robust population cooperation. So these agents are quite robust to noise. One thing I just want to, I think maybe I'll end on this, which is to say that we can take these models and put them into the world of repeated prisoner's dilemma, have them play just that one game over and over again against a whole variety of different baseline players, which I'm not going to introduce. You're either kind of an aficionado of tit for tat, and it's all different variants. And essentially, we can, using our simulation artists without the reciprocal agent, we can we can replicate the prior literature, right? So tit for tat, win, stay, lose, shift. These are good collaborative algorithms. It depends on how much noise there are. It depends on how much repetition there are. But when we add our agent into the mix, without any specific knowledge of tit for tat, it outperforms all of these agents because it can effectively cooperate in a much wider variety of parameters because it has a theory of mind and is able to reason not just about action, but about who's who and use that for its own cooperative abilities. Let's skip this. This also works when agents don't play each other repeatedly. They might just observe and can learn from the play that others make. And so what I'm showing you in the bottom is now no agents interacting more than once with any other agent, but they're observing each other interact. And so then, and the agents can still learn quite quickly whose type is who. And then when we put these agents into the world where they only interact once with another player, again, so there's no repetition except for reputation, these agents can again learn who's who and effectively cooperate. Okay, so I think I'm significantly over time. So I just wanted to kind of wrap up with this idea of some of what I think are some of the foundations for multi-agent common sense: the ability to learn in the moment who's who and how to generalize that notion of cooperate effect, good and bad, to an infinite set of possible situations. I also talked a little bit about some of how we can use evolutionary methods to figure out what makes good cooperators in a much more kind of adversarial type environments. But I also think that more broadly, there's a kind of points towards interesting structures for that humans may be distinct in terms of these capabilities. We can plan based on what we should do, like this idea of we planning, and we also keep track of what we know, so we can keep track of the common or joint knowledge that we might have with other agents. So I'll stop there, and I think take any questions that people have.